The Raiden Network aims to bring fast, cheap, scalable token transfers to Ethereum. In previous videos, we've explained the basic functionalities of the Raiden Network. In this video, we would like to introduce you to the Raiden Network protocol and explain it in greater detail. Before we examine the protocol, let's start by learning what a payment channel is. If you're familiar with this already, check the description below to skip ahead. A payment channel enables a sender to make off-chain payments to a receiver, and is always backed by an on-chain deposit of tokens. When making a payment, the sender signs a balance proof to the receiver. You can think of balance proofs as digital checks. These balance proofs cannot exceed the amount of tokens held on-chain by both parties and are therefore guaranteed to be redeemable for tokens. The advantage of using a payment channel is that payments are potentially orders of magnitude faster and cheaper than on the blockchain. Opening payment channels with everyone is expensive and requires an on-chain deposit, preventing the tokens from being used while held as deposit. This disadvantage is mitigated if users do not need to open channels with everyone that they want to pay, which introduces the need for a network. So what is a payment channel network? A payment channel network lets users pay anyone in the network by using a path of connected payment channels to route the payment. Even though Alice does not have a payment channel with Charlie, she can still pay him by routing the payment through her channel with Bob, and another channel between Bob and Charlie. Within a network, many payments can happen concurrently and independently of each other. But in order to ensure that all users behave fairly, we will need a set of rules to govern the network. So what is the Raiden Network protocol? To do token transfers, users run a Raiden node which follows a set of rules called the Raiden Network protocol. The protocol ensures that all nodes follow the exact same rules when sending and receiving payments. Let's look at an example where the Raiden Network protocol handles a mediated transfer. Mediated transfers use several payment channels to finalize a payment, allowing users to make payments with other users even though they don't have an open channel with each other. In this example, Alice sends a payment to Dave using the channels between herself, Bob, Charlie, and Dave. This payment is locked as a pending transfer, which means that it requires a secret before it can be claimed for tokens. Upon receiving the transfer, Dave requests the secret from Alice. Alice sends Dave the secret, which he uses to unlock his pending transfer. Dave sends the secret to Charlie, who signs a balance proof reflecting the added value of the unlocked pending transfer and sends it to Dave. The protocol is then followed backwards, until the secret is revealed to everyone in the mediated transfer route. But what happens if the transfer somehow fails? If one of the mediating nodes stop responding after the secret has been requested, it would not be possible to unlock all pending transfers before the locks expire. In such an instance, Dave can instead submit the secret to a smart contract called the secret registry. Upon registering the secret on-chain, the mediating nodes can see the secret, unlock their transfers, and send a signed updated balance proof to their counterparty. So to unlock pending transfers off-chain, every participant in a mediated transfer receives a secret to unlock their pending transfers and signs an updated balance proof to their counterparty. If the recipient cannot get the secret off-chain, an on-chain secret registry lets the sender reveal the secret so that all mediating nodes may claim their pending transfers. In order to successfully do a mediated transfer, a path with sufficient capacity is needed. Capacity means that the payment channels used for the payment have sufficient tokens to create pending transfers in all used channels. In this example, Alice wants to pay Dave 3 tokens. So she needs to find a route of connected channels with a capacity of 3 in the mediating payment channels. Suppose all users have deposited 5 tokens per channel and have already made some transfers. The Raiden Network protocol has a full picture of the network and all initial channel balances. It then tries different paths until one with enough capacity is found. Since Alice has 5 tokens and Bob has 5, there is sufficient capacity. Bob has 4 tokens, Charlie has 6, allowing the payment to continue. Charlie only has 2, whereas Dave has 8. This route isn't possible. A refund transfer is initiated, which allows Alice to try a different path to pay Dave. The Raiden Network protocol now tries a path over Earl, Frank, and Gary, which works because there is sufficient capacity in all channels. Since Dave has received the payment, he now requests the secret from Alice, allowing all participants to unlock their transfers and sign new balance proofs to their counterparty. In essence, doing a mediated transfer requires that there is a route with enough capacity from sender to receiver. To keep a record of pending transfers, nodes utilize Merkle trees. A Merkle tree is a data structure where the root of the tree is the hashed value of the data contained in the tree. This data structure allows the root to be a representation of all the data contained in the Merkle tree. For instance, if one data point is removed from the Merkle tree, the root will change. During a mediated transfer, every mediating node adds the mediated transfer to their Merkle tree. As new pending transfers are created, the mediating node checks that the root of the tree matches their local state. In the following example, Bob will mediate several transfers for Alice. To make sure that Alice isn't cheating, he will construct a Merkle tree of all the pending transfers that he expects to claim from Alice. Alice wants to pay Charlie, using Bob as the mediator. Bob now has a pending transfer called Transfer 1, which is locked until the payment is completed. He updates the new Lock 1 to his view of the Merkle tree. Alice then sends another transfer to Dave, using Bob as the mediator. In this transfer, she also sends the root of her own tree. Bob computes the root and sees the same lock as before, so he knows that Alice isn't cheating because Transfer 1 is still pending. Notice that the root of Bob's tree now changes, and that it contains information about both locks. Lock 1 from the previous transfer to Charlie, and Lock 2 from the transfer to Dave. Alice now sends a third transfer to Eric, using Bob as the mediator. And now the benefits of the Merkle tree become clear. It is sufficient that Alice sends just the root and the new transfer to Bob. She does not need to send the previous pending transfers, because Bob can compute the root and verify that Alice has the same number of pending transfers as he expects. Alice now sends a fourth transfer to Frank, using Bob as the mediator. The root Bob receives is consistent with his local state, and he therefore adds the fourth lock to his Merkle tree. Notice how Alice consistently sends no more than a new lock and the root from the previous Merkle tree, regardless of the amount of transfers sent. The protocol continues, and Dave now requests the secret to unlock his pending transfer. Dave receives the secret, sends the secret to Bob, who proceeds to unlock Lock 2 containing Dave's payment, and Bob then sends the secret to Alice, who proceeds to pay Bob. Notice that the Merkle tree no longer contains Lock 2, and consequently the Merkle root has also changed. So to manage pending transfers, nodes keep a local state in the structure of a Merkle tree. Nodes add pending transfers to the Merkle tree when they are making payments, and every node has one Merkle tree per channel direction. Merkle trees allow for a concise cryptographic representation of a large number of pending transfers with a single value, the Merkle root. This property allows the Raiden Network protocol to deal with a very large number of pending transfers. We already learned that nodes can become unresponsive during a pending transfer, and as such, the secret must be registered on-chain from the secret registry. Let's learn how the Raiden Network protocol manages settlements if there are multiple pending transfers. In this scenario, Bob still needs to unlock his pending transfer from Charlie, Eric, and Frank. The only problem is that Alice is offline. Charlie sends Bob the secret to unlock Lock 1 so that Bob may claim his pending transfer. However, Alice has closed the channel and never sends the updated balance proof back to Bob. Therefore, Bob has to resolve the locks 1, 3, and 4 on-chain. Bob starts by registering the secrets which are currently known to him. In this case, the secret of Lock 1, which he received from Charlie. Bob now provides the token network contract with the latest balance proof from Alice, which unlocked Lock 2. The token network smart contract checks that the signature Bob claims is from Alice is authentic. This is possible by cryptographically recovering the address and checking if this address belongs to Alice. After a settlement window has passed, no further balance proofs may be submitted. Then Bob submits his local state Merkle tree, which the token network smart contract checks. It computes the Merkle tree root from the 3 submitted locks. If the computed root matches the previously provided Merkle root, it is certain that the locks that were provided to the smart contract are valid and that they represent the reality of events off-chain. The token network smart contract now needs to pay out the pending transfers to their rightful owners. The smart contract first checks if any of the secrets are known to the secret registry. In this case, lock 1's secret was known, and therefore this transfer belongs to Bob. The pending transfers locked up by lock 3 and 4 were never completed, and therefore expire, refunding them to Alice. So to summarize, there are two main steps for pending locks. Step 1 is to pre-allocate the funds as pending transfers, which are secured by locks. Step 2 is to either unlock the funds to the receiver or to the sender of the payment. If the secret is revealed off-chain, then no on-chain interaction is required. If the counterparty is unresponsive, the blockchain can always be used to guarantee safe transfers. Thanks for watching this video on the Raiden Network protocol. If you're curious to learn more about the Raiden Network, why not try out the software for yourself or check out our documentation? The links are in the description below.